Hello fellow problem solvers, so today we're going to be doing a problem from the 2009 IMO, problem number 5. I suggest you try this problem out for a minimum of 30 minutes, ideally an hour and a half to 2 hours, but not more than 3 hours. This is a beautiful medium difficulty functional equation IMO problem that I would really urge you to try out. It is a problem that can take you to the next level in your functional equation problem solving. And if, on the other hand, you would like to go along with us, I suggest you take 20 minutes and put your first ideas out on paper. And without further ado, let's begin. So the summary of the problem is incredibly short. It's a function from the positive integers to the positive integers such that for all a and b, which are in the positive integers, we have that a, f of b, and f of b plus f of a minus 1 are sides of some non-degenerate triangle. Now what this means is that for every one of these we have ruled that x plus y is greater than z, where x, y, and z are a permutation of a f of b and f of b plus f of a minus 1. And now with that, here's the first idea. One obvious solution that I can think of is f of x equals x. Then we'll have this will be a, this will be b, and this will be b plus a minus 1. The first idea I have is plug in a equals 1, because what we get with a equals 1, we have that 1 f of b and f of b plus f of 1 minus 1 are sides of some triangle. Now, given that these are positive integers and these are positive integer sides, this means that f of b needs to be equal to f of b plus f of 1 minus 1. I invite you to take 5 to 10 minutes to figure out why this is, given that the problem says the functions from the positive integers to the positive integers and 1 f of b and f of b plus f of 1 minus 1 are sides of some triangle. So the reason for that is because, say this was x. What can this be? Well, if it's x plus or minus some c, say this is greater than this. This is x plus some c. But then 1 plus x isn't greater than x plus c. If this was x minus c, then 1 plus x minus c wouldn't be greater than x. So these must be equal. And now that you know that f of b and f of b plus f of 1 minus 1 are equal, can you take 5 minutes and figure out what would you do next? Here's my next idea. Namely, let's prove that f of 1 is equal to 1. If it's not equal to 1, if f of 1 is equals to some c plus 1, where c is a positive integer, say if it's 2, f of 1 is equal to c plus 1, 1 plus 1, c is equal to 1. So in that case, we would have that f of b is equal to f of b plus c for all b in the positive integers. Now what this means is once you pick f of 1, f of 2, and f of c minus 1, all the other values of f are fixed. Now what this means is this function has a maximum, and let the maximum be equal to some number n. Then by plugging in a equals 3n plus 1, we will get a contradiction because we will get that 3n plus 1, f of b, and f of b plus f of 3n plus 1 minus 1 must be sides of the triangle, but f of b plus f of b plus f of 3n plus 1 minus 1, this is going to be less than or equal to n. This is less than or equal to n, which means their sum is less than or equal to 2n, but this needs to be greater than 3n plus 1. Now we get that n plus 1 is less than 0, a contradiction. Now what this means is that this function isn't periodic, and furthermore it means that f of 1 needs to be equal to 1. I invite you to pause here for 10 to 15 minutes and see what would you do next. Play around with the problem, get some other ideas, take the problem further. Here's the next big idea. So the current state of affairs is this. We plugged in a equals 1, and we figured out that f of 1 is equal to 1. Now, it doesn't make sense to look at a is 1 and b is something else, because once you plug in a equals 1, you'll get that 1, f of b, and f of b are sides of a triangle, and this is just always the case. So now let's maybe plug in b is equal to 1 to see what happens on the other side of this equation. So what we have when b is 1, we get the same sort of thing. We get that a, 1, and f of 1 minus 1, f of a are sides of a triangle for every positive integer a. Now what that means, just like previously, it means that f of a is equal to a for all positive integers a. Now I invite you to take 5 to 10 minutes and figure out what this means. So what this means really is that the function is bijective. Namely, it is injective because if f of x is equal to f of y, then we would know that f of x is equal to f of y. This is equal to y, this is equal to x, i.e. x equals y. So it is injective, and it is surjective because if you want to get some number z, you will get that by plugging in f of z into f, because of this. Now why that is important is because our hunch earlier was that f of n equaling n is the only solution. Now proving a bijection it could lead us one step closer to that. We don't know, it could be useful, but we know that we can get any single n out of f. So if we want f of b to be equal to, say, 2, we can get that. What I would invite you to do now is take 20-30 minutes, put all of these ideas we've come with so far together, and try to push the problem further, try to solve it, try to get some new ideas. But I would take 20-30 minutes to really think about the problem condition, and try some stuff out. Play around with it, explore, see how much you can extract from the problem. And here's the idea. So, this is what we have. The problem statement. When we plugged in a1, we got f of 1 is 1. When we plugged in b equals 1, we got f of a is a, and that f is a bijection. Now before I continue on with the idea, I just want to motivate again why we plugged in a equals 1. Why that was the most natural thing for me to do. And the reason I plugged in a equals 1 is because at the beginning of the problem, when we didn't know anything about the function, I didn't know if f of 1 was a million, f of 2 1,000, f of 3 a trillion and 55. I didn't know the relationships between any of these f's, between consecutive f's, between f's in a neighborhood, or anything. So I couldn't really plug in stuff here or here because I didn't know what f of something could be. So that is why I focused on a, plugging in a equals 1, because that would constrain what f of b and f of b plus f of a minus 1 can be. So that is sort of why in the beginning I first plugged in a equals 1 and then I plugged in b equals 1. And the reason I plugged in b equals 1 is because I knew an f. And then I could use that again, like I knew a value that f gave me. Now continuing, I thought, okay, let me try to prove that f of 2 is 2. And let's see, what happens when we plug in a equals 2? Well, we get that 2, f of b, and f of b plus f of 2 minus 1 are sides of a triangle. Now, what this means is that because if this is x, this can't be x plus 2 or x plus 3, 4, because then these wouldn't be sides of a triangle, which means this can only be x plus 1 or x minus 1. And it can't be equal to x because we know this f is a bijection, and if f of b and f of b plus f of 2 minus 1 were equal, we would have b equaling b plus f of 2 minus 1, which would mean f of 2 is equal to 1, which is impossible because f of 1 is 1 and the function is a bijection. So from a equals 2, what we noted is that f of b plus f of 2 minus 1 minus f of b, this is either 1 or minus 1. Or in other words, the absolute value of their difference is 1. And now that we have this, we know that f of 2 isn't equal to 1. And let's say, what happens if it's equal to, say, 3? What if f of 2 is equal to 3? Well, then we know that f of 3 is equal to 2 because f of a is equal to a. But also here we know that f of b plus 3 minus 1 plus 2 minus f of b is equal to 1. Now I invite you to take 10 to 15 minutes and figure out what we can infer from this. I mean, well, we could also infer from this perhaps, but take 10 to 15, 20 minutes even. Here's what we have. We have, in this case, that, say, let's look at it generally actually. Let's say f of b plus a constant c minus f of b. This absolute value is always 1 for all b that are positive integers. Now what do we know from here? And we know that f is a bijection, but here what matters is that it's an injection. Namely, what happens if f of b plus c is equal to f of b minus 1? Well, we only need to look at the first time this happens. If this happens in the beginning, quote unquote, you can imagine f of the sequence, f of b mod c, f of b mod c plus c, all the way till f of b, and f of b plus c, f of b plus 2c, and so on. Unless this happens in the beginning, you can imagine how this sort of f looks like. We get f of b mod c, and then say it goes up by 1. And say that the next one, it either goes up or down. If it goes down, then we have a contradiction, because then we'd have the contradiction, f would not be an injection, we would have two different f's be equal to one another. So if it goes up, it can't ever go down. And if it goes down, it can't ever go up. Meaning this whole thing, like this sequence, is either always decreasing by 1, or it's always increasing by 1. Take 5 to 10 minutes to figure out what this means for this condition right here. Here's what it means. Our claim is that if this holds true and f is injective, then all these sequences, this sequence, this sequence, this sequence, and this sequence, are all strictly increasing. We prove that in the following way. Assume one of them is not, and assume that f of I plus nc isn't always strictly increasing. In that case, it must be that f of I plus nc is going to be greater than f of I plus n plus 1c. Now, if n isn't equal to 0, that means that f of I plus n minus 1c plus 1 is equal to f of I plus nc, and this is also equal to f of I plus n plus 1 c plus 1, which case it means that I plus n minus 1c and I plus n plus 1c are equal, which is a contradiction. So it must be the case, if it's not strictly increasing, then f of I must be greater than f of I plus c, and this in turn must be greater than f of I plus 2c, and so on. This is a strictly decreasing sequence. But if we make this k, then f of I plus nc is going to be k minus n. And if we just make n greater than k, we'll get a contradiction. We'll get that f of some positive integer needs to be a negative integer, which is false, and because this is not in the codomain of the function. It's not in the range of the function. So now with that knowledge, let's turn back to our original problem. Namely, so we say, let's say what happens when f of 2 isn't equal to 2. Say f of 2 is equal to 3. Well, this means f of 3 is equal to 2. And then what do we get? From our, we get f of b plus f of 2 minus 1 is equal to f of b plus 1 for every b. Given this is 3, we get that f of b plus 2, or no, is this b plus 2? Plus 2 is equal to f of b plus 1. Now would f of 1 equal 1? Now what this means is that f of 2t for every even t is going to be equal to f of 2t minus 1 plus 1 is going to be f of 2t minus 2 plus 1 is going to be equal to f of 2t minus 4 plus 2 is going to be equal to, all the way till, f of 2t minus 2 plus twice this, t minus 1, which is equal to f of 2 plus t minus 1, which is equal to, because f of 2 is free, this is going to be equal to 3 plus t minus 1, t plus 2. And in a similar way, we will get that f of 2t plus 1 is going to be equal to 2t minus 1 plus 1. It's going to be equal to f of 2t minus 3 plus 2, all the way till f of 2t plus 1 minus 2t plus t, which is going to be equal to f of 1 plus t, which will be equal to, because f of 1 is equal to 1, this will be equal to 1 plus t. Now, is there a problem with this? And the answer is actually immediately looking at it now, yes, there is. And that's just from playing around. What we would get is that f of 4, just from here, we'd get that f of 4 is equal to, okay, f of 2 plus 1 will be 4. But we'll get that f of 5 will be equal to f of 3 plus 1, which will be 3, in contradiction because f of 2 is 3 and the function is bijective. So this is how we can know that f of 2 isn't equal to 3. And now we just need to generalize this. I invite you to pause 5 to 10 minutes and try to generalize this. Try to take these bits and pieces I've given you and put them together in this puzzle. Here it is put together. So we have this. F of 2 is x0, and that means f of x0 is 2. Now what does this mean? Well, let's plug in here. Let's plug in x0. And what will we get? We will get that f of x0 plus 1, which is 3, is going to be equal to f of b is x0 to x0 minus 1. Great. Now let's also plug in 2, and we'll get that f of 2 plus 1 is going to be equal to f of 2 plus 1 is x0 plus 1, and this will be equal to f of x0 plus 1. Now also from f of x is x, if we plug in x equals 2x0 minus 1, we will get that f of 3 is 2x0 minus 1. And now if we plug in 2x0 minus 1 here, we will get that f of 2x0 minus 1 plus 1. This is equal to 3 plus 1 is 4, is going to equal f of 3x0 minus 2. Now, if you can see where I'm going with this, I would invite you to pause for 5 minutes. And namely, via induction, what we have is f of nx0 minus n minus 1 is going to be equal to n plus 1. Now, how do we prove? Say this is true for n1n, assume it's true for n, then for n plus 1, we will also get f of n plus 1 will be equal to nx0 minus n minus 1, which we'll use later. But we also get, if we plug in b is equal to nx0 minus n minus 1, we'll get f of nx0 minus n minus 1, which is plus 1, n plus 1 plus 1 is equal to f of nx0 minus n minus 1 plus x0 minus 1, which is f of n plus 1 x0 minus n. And this is equal to n plus 2, which proves our inductive hypothesis, which means that f of nx0 minus n minus 1 is equal to n plus 1, and also f of n, let's say n plus 1, to make things simpler, is equal to nx0 minus n minus 1. Now what we know is that f of x0 is equal to 2. So now let's plug in n plus 1 is x0. So we'll get that f of x0, which is equal to 2 on one hand, is equal to x0 minus 1 times x0 minus x0 minus 2. And what we get from here is that 2 is equal to x0 squared minus x0, and then this is a minus x0, and then this is a plus 2. In other words, x0 squared minus 2x0 is equal to 0, and we get x0 minus 2 is equal to 0. In other words, x0 is equal to 2, which means that f of 2 was in fact equal to 2. And now from here, we get that f of b plus 1 is equal to f of b plus 1, b plus 2 minus 1. And now from here, we can infer via induction that f of x is equal to x for all positive integers x. Now let's bring this all together and write up a solution. So we had this function, and then what we did is plug a equals 1, which implies f of b is f of b plus f of 1 minus 1. And from here we said if f of 1 is not equal to 1, then it follows that f of b is equal to f of b plus c for some c that's a positive integer, which implies that the function f is bounded by some m, which implies a contradiction, plugging in a equals free m, which will give us free m greater than m plus 2m, which is greater than f of b plus f of b plus f of free m minus 1. And now from here, we know that f of 1 is equal to 1. And then what we do is plug b equals 1, which implies that a is equal to f of a for all positive integers a. Now from here, we know that if f of x is equal to f of y, this implies that x equaling f of x is equal to f of y is equal to y, i.e. x equals y, i.e. f is injective. Now from here, assume f of 2 isn't equal to 2. Now plug a equals 2, and what we get is f of b plus minus f of b plus f of 2 minus 1, all of f, that absolute value difference is equal to 1 for all b. Now put f of 2 equal to x0. Actually, instead of assuming, just let f of 2 equal f0. And then we have, which is unequal to 1. And then we have f of b plus x0 minus 1 minus f of b. This absolute value is 1. And now what we do is calculate f of n times x0 minus n minus 1. And now we prove that f of b plus x0 minus 1 is equal to f of b plus 1. We do this by assuming there's a b such that the converse holds. And now this implies that taking the minimum such b, let that be equal to b0, we'll have that f of b0 minus x0 minus 1 plus 1 is equal to f of b0 is equal to this. Assuming this is in the domain, but because this will give us a contradiction, i.e. it would give us that x0 is actually equal to 1, this implies that b0 is less than x0 minus 1. And now what we do from here is, via induction, we have this holds. It holds for n equals 1. Assume it holds for n equals t. And then for n equals t plus 1, we have f of b0 plus t plus 1, x0 minus 1, is going to be equal to f of b0 plus t times x0 minus 1 plus or minus 1. If it was plus 1, then this would imply a contradiction because via the inductive hypothesis, plus 1, this already equals f of, so actually minus 1 will be a contradiction because this is smaller, because this already equals f of b0 plus t minus 1, x0 minus 1 by the inductive hypothesis. And now we know that the inductive hypothesis is true, i.e. we will have f of b0 plus n times x0 minus 1 is equal to f of b0 minus n. Now, what we have from here is a clear contradiction. Once n is equal to f of b0, we would get that f of something is going to be equal to 0, which is a contradiction because 0 is not in the range of the function. And the possible is because 0 is not in the possible range of the function. And now from here, now all we know is that this thing right here is always true. And now the next step is, now we know this, which implies f of b plus n times x0 minus 1 is equal to f of b plus n, which for a specific b, namely b equals x0, this implies this, which further implies given f of x is x, this implies, and now, because this is true for every n, now we just plug in n plus 2 equals x0, and what this gives us is f of x0 is equal to x0 minus 1 times x0 minus x0 minus 2. This thing is equal to 2. The 2's cancel out. And what we are left with is x0 minus 2 times x0 is 0, which implies, because we are in the positive integers, that x0 is equal to 2, i.e. f of 2 is equal to 2. And then from our original thing, namely this implies that f of b plus n is equal to f of b plus n, which implies that f of x is equal to x for all positive integers x is a solution. Furthermore, it's the only solution, and now we plug that into the original, check that it works, and we have that a, b, and a plus b minus 1 must be sides of a triangle for all a and b, which are positive integers. Now this is true because a plus b minus 1 is greater than a and b, but it's less than a plus b, which means that the only function which satisfies our problem statement is the function f of x equals x for all positive integers x. And as always, thanks for problem solving.